Okay, well, thanks. This is the second part of my mini course on thin groups as monodromy groups. Let me just sort of recall from last time, just to sort of put us in context. So last time, so we saw that families of varieties, and in particular, I think everything I'm going to talk about today is about algebraic curves. Families of varieties give rise to monodromy groups in GLNZ, or especially SP2GZ, which is the case when we're studying families of genus G curves, as I'll largely do today. And what we saw is that which are sometimes thin, and I gave a couple of examples, and sometimes not. So in other words, both cases can actually happen. And just to kind of summarize the sort of typology of this dichotomy between these two cases, without stating any precise theorems, maybe largely because I don't know any, I would say that the cases where the monodromy is finite index, maybe you would say very loosely, as actually came up in Allen's talk, is where you have lots of unipotents in your generating set for the group. And algebro-geometrically, the reason that would happen is that you would say, let's say, have lots of semi-stable reduction. So in the case of families of curves where the reduction is the bad reduction is as unbad as possible, just like a simple node, you're going to actually see lots of transvections, and that's going to help you in your goal to generate a finite index subgroup by the theorem of Vega-Ramana or other things. The other thing I would say is that it seems in practice that the situations where the monodromy is in fact finite index are more free situations, like families of curves which can be deformed in more directions. So I would say here, I would say more deformable. And by contrast, I would say the thin cases in practice appear to be more rigid. For instance, the Teichmüller curves I mentioned, which give a very handsome family of families of curves with thin monodromy groups, those actually don't deform at all. They're rigid. They have no holomorphic deformations. The Norrie's example has one dimension of deformations. But in general, maybe this is another piece of evidence in favor of the philosophy that somehow the more generic you are, the less likely you are to have thin monodromy. But in this case, the word generic is not meant in any precise algebro-geometric sense. Okay, so so we have these monodromy groups. Yeah, Lior? Well, the groups are, it's not really, it's the rigidity of the family, not the rigidity of the group. So yes, more rigid families give less rigid groups. Okay. Well, in Emmanuel's like the large sieve let less stuff through. I mean, all these notations are very, can be confusing at times. Okay. So we have these groups, and sometimes they're thin, and sometimes they're not. So what I want to talk about now is super strong approximation for monodromy groups, which if all monodromy groups were finite index, you sort of wouldn't need new theorems, but since monodromy groups can be thin, in order to be able to talk about super strong approximation for monodromy groups, you need to be able to talk about super strong approximation for thin groups, which is what much of our discussion here has been about. So what I want to talk about in this section is a reason that algebraic geometers like myself and Emmanuel, who's an honorary algebraic geometer, and Chris, a reason that people like us would actually need to carry out super strong approximation on monodromy groups. So I'll spend the first part of my talk today talking about this paper of the three of us, which I guess will probably come out in 2012, right? That's safe to say. Okay. But it exists in the archive now with an earlier date on it. Okay. So I'm trying to not kill a tree, and I downloaded my notes. So we'll see if this, it's a little experimental, but we'll see if this works. I mean, but I didn't have to get a new iPad to do this. That's the point. So, first I need to introduce a basic invariant of algebraic curves, which is called the Gonality, because that's sort of what this paper is about. So, if X is an algebraic curve, well, in some sense, its most basic invariant is its genus. That's a purely topological invariant, just when you look at it as a zoom-around surface, what is its genus? But if you want to get a little bit more refined by that, you can ask about the Gonality, which was usually denoted gamma, and we'll say gamma of X is the minimal degree, or is the minimal integer d, such that there exists a degree d map from X to P1. So, for instance, Gonality 1, that means you have a degree 1 map that is an isomorphism to P1, so that's the same thing as saying your genus 0. You are just projective space. Gonality 2 is the same thing as being hyperelliptic. So, I mean, in algebraic geometry, a hyperelliptic curve is precisely one which is a double cover of P1. So this word Gonality is sort of a generalization of the very useful notion of hyperelliptic as a quality on curves to sort of looser and looser conditions on the curve. But this is really is an invariant of the complex structure on the curve. You can't read it off the topology. It really, as you move around the moduli space of genus G curves, some things have higher Gonality and some things have lower Gonality. Why do you care about this? I think I'm not going to sort of go into the whole story so much, but let me observe that you probably know that genus 0 curves, like P1, has lots of rational points. A hyperelliptic curve, if it's high genus, does not have so many rational points by faultings. But if I write down, so e.g., this is going to be y squared equals f of x, if this curve is over q or something, it probably doesn't have a lot of rational points. The analytic number theorists can observe that a high degree polynomial is not likely to take too many square values, and in fact, faulting proves that it doesn't. On the other hand, this guy does have lots of points over quadratic fields, because I can just plug in any old rational number for x that I want and then take its square root, and I'm going to get a point over a quadratic field. So this has lots of points over quadratic fields. So the application of studying Gonality to arithmetic geometry is that we say, let's see if I can get this right, because I didn't actually state this theorem precisely in my notes, but, and then I guess this is sort of, I should say, Abramovich and Volach, and Fry, and probably faultings too, is that if the Gonality of X is bigger than or equal to twice d, then X has only finitely many points over number fields of degree less than or equal to d. So this is pretty cool. This is like saying, like, if your curve has infinitely many points over quadratic fields, not a single field, but over all the quadratic fields put together, then its Gonality is at most 4, for example. So this is kind of there's a whole industry, of course, of proving finiteness theorems on rational points. In many cases, situations where there's a finiteness theorem on rational points, there's even a finiteness theorem for points on fields of bounded degree, and in some sense, Gonality is the geometric invariant that allows you to get at questions like that. Say again? Yeah, because what can happen is if you have a map to an elliptic curve, the elliptic curve is hyperelliptic. So you can kind of have a degree d map to an elliptic curve, and that elliptic curve might have infinitely many rational points, each one of which pulls back to an extension of degree 2d. So that's why you need to say 2, because elliptic curves annoyingly can have infinitely many points. Oh yeah, sorry. Yeah, that's a you analytic number theorists who care what the exact value is. It's very strange to me. Okay. Yes, that is right. So actually, before I talk about the general setting in which our theorem takes place, I want to talk about a setting in which everything I'm going to talk about is already understood, just because it's going to lead into what I want to talk about in the second part of this talk. which is a very nice example of monodromy, which is, let's consider the following case. The modular curve x1 of n, which parameterizes elliptic curves together with an n torsion point, over x of 1, which is just parameterizes elliptic curves. Or if you like the hyperbolic point of view, I can write this as upper half plane mod gamma of 1, otherwise known to normal people as SL2Z. And then mapping to that as the quotient of h by the congruent subgroup gamma 1 of n. So that's a finite cover, and like all finite covers, it gives you a monodromy representation to a permutation group, as we discussed in the first part of yesterday's talk. In this case, the fundamental group of the base is x of 1. You have to be a tiny bit careful. I didn't say these words last time, but every time I say fundamental group, of course I mean this in this sort of appropriate orbifold sense. So if you think of, I mean, you definitely need to think of this as a stacky thing whose fundamental, it's a contractible space, mod SL2Z, so its fundamental group had better be SL2Z, even if you mistakenly think of it as a line. So this gives a monodromy rep from the pi 1 of the base, which is SL2Z, to, and now I'm going to write this, but I'm going to immediately erase it. It sort of permutes the fiber of this map. Well, the fiber of this map just parameterizes elliptic curves with an n torsion point in this elliptic curve. So the fiber of the map is just the n torsion points of that elliptic curve, which we denote E brackets n. But you can probably guess that the image of this map, it doesn't permute those n torsion points arbitrarily. It is the linear action. That's sort of the only thing that it can be. So I will just go ahead and write. It goes to the linear group. And of course, how does SL2Z act on this group, which is isomorphic to d mod nz squared? Well, it's going to act via its congruence quotient. So I mean, this is sort of the world's fanciest way to write that SL2Z maps to SL2Z mod nz. And in some sense, like, I mean, I'm not saying anything here that's sort of not obvious, but I'll just remark that we said the connectedness of the cover is in correspondence with the transitivity of the action. So in some sense, by some sort of weak version of strong approximation, this action is transitive, and that's in correspondence with the fact that you know very well that these modular curves are connected. So here is another fact that is much less obvious about these modular curves, which is that, oh, am I going to say this now? Oh, it's not on my notes, but I think I will say it anyway. So in fact, the gonality of x1 of n is bounded below by a linear multiple of the degree of this cover, which in turn is about, I guess, is about n squared. So, so that's a remarkable fact, and let me explain why it's true as a part of a more general story. So in some sense, you should think of, as I just said in words, connectedness of x1 of n is a consequence, a rather weak one, of strong approximation, as I just explained. And growing gonality is a consequence of super strong approximation. Which in this case, of course, follows from Selberg. So, so let me explain how that works, and I will now move to kind of a more general picture. Yeah, it's like n squared. For x1 of n, it's like n squared. If I wrote the full x of n, everything I said would still be correct if I wrote x of n, and then it would be like n cubed. It's just one point, and actually, because in the application, I'm not going to do the Gala cover, so I wanted to have a non-Gala cover on the board. But I mean, what I'm saying would apply to sort of any family of congruence modular curves. I just happen to have chosen this one. Okay, so more generally, let me let U be my favorite kind of algebraic. Well, actually, I think I'm just going to say U an affine curve. U prime to U finite cover, and S a set of local generators, by which I mean generators which are in those special consequences, conjugacy classes I talked about last time, corresponding to little loops around the punctures in U, for pi 1 U, which since I made this an affine curve is actually a free group. So nothing is really different with surface groups. I just don't want to kind of say free group or surface group all the time in this discussion. So let me, well, maybe actually just to sort of avoid having to say more stuff. Actually, I'm not even going to say local generators. I'm just going to say generators. It's a free group. It has generators. We don't care what they are. So what's going on here then? It's a free group generated by S. So you have a free group generated by S, otherwise known as the fundamental group of the base located at some base point. And it's going to act by permutations on the fiber of U prime over this point. So I'll just remark this is a finite set. So of course this can be described by a Cayley graph, or more precisely by a Cayley-Schreier graph, right? If I have a free group acting on a finite set, I can just make a graph, which I will now make. I think I'll make it with a new, longer piece of chalk. There's not much. I'm not sure we're going to make it till Friday, actually. Oh, I see. Oh, I see. There's more up here. Okay. This is good. So maybe I'll just call this G U prime US, the graph with vertices, this finite set, and V connected to SV, and maybe to be safe, I'll also write S inverse V, just to make this not a directed graph. I mean, because the free group, because the elements of S act on this set, this exactly makes sense. And then the statement of the statement that gives us the growing gonality here is precisely that this family of Cayley-Schreier graphs forms an expander family. So these are the graphs associated to the finite covers. And the slogan here, and again, the connectedness of this graph, which is the same as the transitivity of the action, is the same thing as to say that this curve is actually connected. So this is the shadow of a more general slogan, which says that the geometry of this graph is a model for the geometry of the algebraic curve U prime. And I guess the way I think of it, there's probably no good will come of my trying to draw this picture, so maybe I'll say it in words. If you imagine U is being fixed, and we're looking at a sequence of larger and larger covers. After all, if we're going to be in this world of expanders, we should be talking about a sequence of graphs with more and more vertices, right? So I should take a sequence of covers of higher and higher degree. Oh, so maybe I should actually physically say the words that the size of this fiber is, by definition, which is the number of vertices of the graph, is the degree of U prime over U, so increasing the degree of the cover makes the graph bigger. This graph can actually be embedded in the Riemann surface U prime, and in some sense, U prime has like a lot of little copies of U, which I think of as sort of stretched over that graph, like a skeleton. And so as the degree gets bigger and bigger, in some sense, more of the geometry of U prime is controlled by the combinatorics of that graph, and less of it depends on what U looked like originally. So as the degree gets bigger and bigger, in some sense, the extent to which these two geometries are supposed to resemble each other gets better and better. I don't actually have in mind like a sort of like literal like limiting statement or something. That's just sort of how. I'm going to tell you, yeah. And that's, by the way, that the relation between those two things is not due to us. It's due to Li and Yao. I mean, in some sense, a lot of this, as you'll see, is sort of combining off-the-shelf ingredients, but that were sort of on a lot of different shelves, possibly like actually in different stores. So in particular, let me give a very direct way, and I hope I say all the names that I should say, by work of Brooks and Berger and Borgan, Gambard, Sarnak, to go to the infinite volume case. We can say that the spectral gap of U prime, so what I mean by that, U prime is a Riemann surface, so I mean a differential geometric thing. I mean the spectral gap of the Laplacian acting on that thing. So this is bounded below by a constant multiple of by the spectral gap of this graph, where this, of course, is in terms of the usual discrete Laplacian. So this is the sense that I'll use of this statement that the geometry of the graph is a model for the geometry of the Riemann surface. Like, I mean, and it kind of makes sense, right? If you imagine a denser and denser skeletal graph, its Laplacian is somehow going to approach the, I mean, but, yeah, that's why it's not a perfect analogy. Nonetheless, this is true. So, so what we've got now is if we have a family of covers, which is expander, now we have a family of curves. Now you actually have a geometric statement. We have a family of curves, which is an expander in the sense. Do we say that for curve? I don't even know if that's something that's said, but which has a spectral gap for its Laplacian as you go. Yeah, there's a uniform spectral gap for this family of curves. Yeah. Okay, so now I think I'll state a theorem, which is a theorem in our paper. By the way, when did I start? Chair or otherwise? I sort of lost track of it. Did we start at 35? 35. Okay. So let me say a theorem, which is in our paper. Wait, I forgot if I wrote these guys' names on the board before. Just in case I didn't, I'll do it again. So let U a curve, and now I'm going to have a sequence, as I hinted at before, a sequence of finite covers of U, and let S be a generating set for the pi 1 of this curve. Maybe to be really emphatic about it, I'll sort of say the pi 1 of the complex points of this curve, since I'm thinking of it as an algebraic curve. And suppose that these Cayley-Schreier graphs, UI, US, are expanding. So maybe in the middle of stating this theorem, let me say that actually in our paper, there were situations at the time our papers were written, we sort of knew less general theorems about expansion at the time, and actually this condition is stronger than we needed for the applications we were trying to get. So you'll see there's another condition called Esperantist in our paper. I do think it's actually quite interesting to think about weakenings of expansion that are useful in the geometric context, but today I'm not talking about things that are stronger than strong, but not as strong as super strong. We're just talking about super strong in this conference. So I will say what happens if you have an expander, which is sort of the best case scenario. So suppose these Cayley graphs are expanding, then, in fact, the gonality goes up linear with the degree. So this is the fact that I stated about x of n over x of 1. And in some sense, this is not special at all to that case of moduli of elliptic curves. So I will say that for x of n to x of 1, this was, I think, the very first proof, as Peter told us, was from Zograff, and then also Abramovich. So in some sense, what we do is sort of an extension of their method using using the new techniques. Say again? So an upper bound, the thing is upper bound, you can upper bound in terms of the genus. And the genus is easy to upper bound topologically. So yeah, I guess it's, and I thought that would also be linear, that's clear. Oh, that's an even better reason. Yes. Yes, so, but I mean, it's not the same constant. Okay, so let me say something about how this works. So sketch of proof. So first of all, you use a result of Kellner to tell you that the genus grows. That's the first thing that you need. So the genus grows linearly. Well, it's bounded by, all constants are going to be 1 in this talk. I'm not going to keep writing them, sorry. But it's bounded by, okay. That's what I have in my notes, actually. Anyway, so it's bounded by the spectral gap times the degree. So in particular, if the spectral gap is bounded away from 0, which is going to be the situation where we have expanders, then that tells you that the genus grows linearly in the degree. And just to give sort of some kind of physical sense of why that would be true, let me sort of try to give you a mental picture of how you know that the genus grows at all. Like, how do you know it doesn't stay 0? Well, if it were to stay 0, so e.g., if g, sorry, I should say g of ui, if g of i of u of I were always 0, remember I told you that these graphs actually embed in the surface, and a graph that embeds in a sphere is a planar graph. So you would have a sequence of planar graphs of larger and larger degree, but such a family cannot be expander. I mean, that's sort of contrary to the very nature of expanders. They sort of have to, the random walk has to be able to sort of spread very quickly, and if you're stuck in a plane, you just can't get very far away from where you are. So that's the world's worst proof of that. But it should make you feel that it's true, I hope. So we couldn't expand. It would force lambda 1 to be decreasing. Okay. So that's one ingredient. The next ingredient, and by the way, somehow this sketch is it's gonna make this look easier to prove than it actually was. So if you look at the paper, there is actually some work, but I mean, from a distance, the conceptual material is actually quite simple to explain, so I'm going to do it. So here's where gonality comes into the picture. An analytic result by Li and Yao tells you that the gonality is bounded by, again, the spectral gap times the genus. So if you know the genus is growing linearly and you still have this, that the spectral gap is bounded away from 0, oh, right, so yes, sorry, good, because I just wrote lambda 1 without saying anything. So this is the excellent point. So this is about, that's right, this is about the graph. It's about a theorem about graphs embedded on surfaces. Now the graphs have been left behind, and this is a theorem in differential geometry, and it's about the lambda 1 of ui. But then combining that with this statement over there, given that these graphs are expanding, so are you have a uniform spectral graph here as well, and then you're finished. Maybe. Yeah, so there is, yeah, it's not 1, it's not literally. Yeah, and actually this is a very, so I want to speak to this point in 1 second that you raised, Emmanuel. So let me say, I'll just finish, but in some sense I have finished. So this is again bounded again with a constant by u1 of the graph by what I said before. And then, so we're finished. So 2 comments. One thing we really don't understand is the dependence on the base curve u. So I'll just write this as a question. I mean this part. So question, to what extent can this be made uniform as u varies? But I mean, we should fix the topological type of u. We shouldn't let the group change. So I want to say as u varies, let's say over mgn, like as it varies among the genus G n-pointed curves. I think this seems possible, but we just don't know. So and I think that's actually somehow a central question that would make the theorems like much more flexible to apply. So I'll sort of box that. But the other thing I was going to say, of course, is that this part of the theorem sort of takes as input some expanding graphs and gives you an output, some geometric statement about gonality, which we use in the paper to derive theorems about rational points via the theorem I stated earlier. Well, where do you get the expanding graphs? And that's where we need super strong approximation, of course. Super strong approximation is like a machine for sort of handing you like a big bushel of expanding graphs. So I'll just give an example of one. We write a bunch of sort of various applications in the paper. I'll just sort of write one and explain to you where that works. So theorem, let A over Q of T be an abelian variety. In other words, a good way to think of this is as T varies over rational numbers, you can think of this as like a family of abelian varieties over Q. Just as in Allen's talk, there was kind of a family of representations. I mean, a representation over a polynomial ring is the same thing as a family of representations that you can specialize to different things. And then the claim is that for all L, which are for all primes L, which are sufficiently large relative to D, let me just go over to the other side. The set of T, of algebraic numbers T, so now I'm going to let T be in Q bar, such that, okay, now this might be a little hard to parse, but I'll write it down and then I'll say it in words. Okay, so I've specialized the T, so I've got an abelian variety over some number field, don't know what it is. And I'm going to look at its L torsion points, which are going to be defined a priori over some extension of the field generated by T. Right? If you have an elliptic curve over Q, for instance, and you look at its torsion points, they're usually not defined over Q. They're usually defined over some bigger field. But of course, they might be defined over Q, and that's the case that we're interested in number theory. So we're going to look at just those ones which are defined over the same field as T. So maybe I should say like T0 to make it clear that now T0 is an actual number that I've chosen, and this is a number field, not the function field Q parentheses T. Okay, so we're looking at this set of points, which you might expect in some sense to be small, because it's not usual to be able to find L torsion points over the same field the abelian variety is defined over. And we're in fact looking at the set of T naught such that this contains a non-trivial point. And then the conclusion is that this set contains only finitely many points of degree D over Q. In other words, if I make this L big enough, I can arrange it so that there's only finitely many points over all the union of all quadratic fields that have this property of having a torsion point in this family. So something that we think should be rare actually is rare. And what are the families of covers that pertain to this? Well, I already told you that then when we study x1 of n over x of 1, which is parameterizing the torsion points of a given degree on an elliptic curve, we're just taking the usual SL2 and modding it out by n. So the situation is very similar here. I'm not going to sort of really justify them because I don't want to give an algebraic geometry talk. I'm just going to sort of say what's going on. The relevant covers are as follows. You have a monodromy representation, as always, from pi 1 of your base to, in this case, it's going to be sp2g z. But you're going to compose that now, just as we mapped SL2z down and we let it act on z mod nz squared. Here we're going to let this act on z mod lz to the 2g, which are the algebraic L torsion points of this curve. So let me just write the action. I mean, it permutes them, but of course it permutes them in a symplectic way. So I'll write it. This goes to sp2g z mod lz. I will say they are given by. Right, so now I've got a map from the pi 1 of u to a finite group. So a point stabilizer is giving you a finite cover. And what I need is for the resulting Cayley-Schreier graphs to be expanders. But what is that? That is exactly saying, I mean, those Cayley graphs are exactly the ones where I take this monodromy group and look at the resulting graph mod L. So, so to know the corresponding graphs are expanders, follows from super strong approximation for the monodromy group of this family sitting inside sp2gz. So just to say a word about our progress towards thinking about this and proving it, it was sort of funny because, you know, as algebraic geometers, to be quite honest, like, to me, like, monodromy is a profinite thing, right? I mean, my monodromy groups are always in sp2g z hat. So I think, Chris, maybe you would say the same was true for you, or used to be true for you. No? Okay, whatever. It's just me. Yeah, Yan. Oh, sorry. So I blew it here. In this case, U would be, so this looks like a family of a billion varieties over like the irrational curve, like P1. But there's going to be some values of T where this actually has bad reduction, and I have to take them out, because I always have to be talking about a fibration. So U, excellent question. So U here, the base, is going to be P1 minus T such that AT is non-smooth. So we strip those out, and then we get the same base I always get, a punctured sphere. So I mean, it looks different. I mean, it's easier in the isotrivial case. You're right, you do have to say something about that case. I mean, I'm papering over. I mean, a hard part of the work is actually sort of showing what the monodromy group is. Yeah, if it's literally trivial, it's just 1 a billion variety over Q, and then it has only finitely many torsion points. So if you make L big enough, it doesn't have any. So it's not true for an interesting reason, but it's still true. Yeah. So maybe I wrote this too simply. I sort of tried to write a sort of version of this that's like more simply stated. So you have to be a little bit careful in that case. I mean, but this is not literally the same statement word for word as in the paper. I tried to write it more simply, and I didn't think about that case. Right, so you have to, so a big part of the work is actually saying the monodromy group, it need not actually be dense in sp2g, and that's right, so you have to do that separately, and then you say something else. Like you don't, I mean, you're right, you don't say literally these words that I wrote on the board. On the fly? Probably not. What? Okay. Well, so that's the kind of thing, so, I mean, that's actually, that's, wait, do we end up calling that an appendix, or is that, it's a, it's, but that has to be shown. That's not obvious. So this is sort of a sequence of things that goes back to Serre, like proving big monodromy theorems, and it's one of those things where we write a lot about this in the paper. Sort of Serre says everything I say for number fields is true for finitely generated fields over number fields, but there is some stuff to check, which we check in the paper, and that's what you have to do. So I mean, that's a good example of like the kind of work that I'm papering over, but is actually there in the paper. Ah, okay, so this is another thing that, definitely not. Definitely not. You need to show it satisfies the condition of Pieper and Szabo's theorem. And then we use the slight, and you need to show it satisfies the condition of Pieper and Szabo's theorem, which is what exactly? That it's perfect. And then we actually use a condition that from their paper that's slightly weaker than expansion, but is enough. So yeah, so yeah, but that is an excellent point that actually, at this point, I'm sort of, the theorems, this theorem I stated up here is different from the paper, and in the paper there's a weaker condition which is actually known for SP2 GZ. But I mean, in some sense, this is sort of the Platonic ideal of like how the, I mean, and this statement is of course true as written. It's just a question of whether you actually know the expansion. Okay. So I think that's, so I think that's what I'm going to say about that. And now I sort of was like, so my plan was to sort of say more speculative stuff for the end, and there was like a host of different things I could talk about, but I think Kurt's talk inspired me to, among those things I could talk about, sort of choose one of them. So I want to talk a little bit about the mapping class group, and then so somehow, as it happens, like all three of our talks today or this morning are about the mapping class group. We didn't really do that, or have the mapping class group as a character in them. So let me just kind of now be philosophical for a bit, but hopefully with some content, about what we should mean and what we should ask about strong approximation and super strong approximation for mapping class groups. So let me again recall this example of x1 of n mapping to x of 1 that I mentioned before. There you had in x of n to x of 1, this is our canonical picture of what a congruent subgroup means. What's going on, you have SL2Z. As I said, it's acting on z mod nz squared, but I want to think of that as Homs from z squared to the finite group z mod nz. And then it's crystal clear how SLNZ is supposed to act because it acts on this z squared. That's its very reason for being, to act on z squared. So, and we study this action. But now there's a more general way to think of this, which is as follows. Let me let, following Allen, let me let sigma gn be a surface of genus G with n punctures. I'll write pi gn for its fundamental group, which is going to be free unless n is 0. And finally, I will write gamma gn for the mapping class group of type Gn, which is just the isotopy classes of diffeomorphisms of this surface to itself. So as Emmanuel mentioned, this is a group that low-dimensional topologists know a lot about. We don't need to know a lot about it for what I'm going to say now. So, so one thing to note is that, of course, a diffeomorphism, and even up to isotopy, acts on the fundamental group of the surface. So the reason for being for the mapping class group in some sense is to act on pi gn. So gamma gn acts on pi gn, and in fact it has a nice description as a certain subgroup of the automorphism group of this discrete group. So thus. And now we can do the following thing. We can take this whole picture. You see, an example of that is given by, so e.g., gamma of, well, what's pi of 1, 0? That's the fundamental group of a genus 1 surface with no punctures. And we know what that is. That's z squared. Equals z squared. And you may not be so surprised to learn that gamma of 1, 0 is SL2Z. And so this story is revealed as an example of a more general story where I just say, oh, yeah, that's true. Yes, that is a good point. It's really an outer action. So let me write, so in this case, it doesn't matter because z squared is a billion, and I will explain why I can. So let me say this outerly. So in general, so that's exactly right. So let me say what we have. In general, for every finite group G, this mapping class group acts on the following set. I'm going to take homomorphisms from this fundamental group. Now, gamma gn, as Ian points out, doesn't quite act on this. It acts on it by outer automorphisms. So you would like to say, okay, it acts on the homomorphisms from this guy to this finite group. This is a finite set, right, because this is a finite generated group. So this set here is finite. But in order to make this correct, let me just mod out by conjugation. And then it doesn't matter which inner automorphism I modify by. So, so we have gamma gn acting on a finite set. And actually, one example of this is related to the example that Kurt said in his talk yesterday. So let me link that up. E.g., when g equals n equals 1, and G is the symmetric group on D letters, we get an action of gamma of 1, 1 on the homomorphisms from pi 1, 1 to SD. But now, pi 1, 1, remember, is the fundamental group of a once punctured elliptic curve. So maps from it to SD have to do with degree D covers of an elliptic curve punctured at just one point, which is exactly, I'm not making this genus 2 hypothesis, but I mean, contained in here is the set that Kurt was talking about in his talk. So this is an example of this kind of action. So I'll just say, as we saw in Kurt's talk. And this mapping class group, if you don't like calling it gamma 1, 1, you can also call it SL2Z because it is. This is sort of this amazing fact that somehow if you have an automorphism of the free group on two generators, you can tell what it is just by what it does in the abelianization, just by its image in SL2Z. And so let me make two comments about this picture before I'm just going to close by sort of asking various questions, none of which I have any idea about the answers. So remark one, you'll note that in a situation like this, where we're acting on where we have a linear group acting on an abelian group, the stabilizer of some point in z mod nz squared is a congruent subgroup, right? That's the gamma 1 of n. That's what we call the subgroup of SL2Z that fixes one of those points in z mod nz. So I think typically the point stabilizers in this action are, and maybe I'll say they are sometimes, called congruent subgroups. The analogy is not really exact, but of gamma g of gamma GN. And sort of a question that's occupying a lot of attention, I think sort of somehow after people not thinking about it for a while, sort of Thurston started thinking about it and brought it to light again, is the question of whether to what extent mapping class groups have the congruent subgroup property. And maybe I'll sort of make as an aside that in this sense, e.g., gamma 1, 1 has the congruent subgroup property. And this was, I think, really first proved by Asada, and then it was refined by myself and Ben McReynolds. So now, I mean, you could all go home and say that at this conference, Ellenberg told you that SL2Z has the congruent subgroup property. But which it does, like in this more generalized sense of I mean, SL2Z in its manifestation as gamma 1, 1 really does have the congruent subgroup property. In its manifestation as gamma 1, 0, it really does not. I mean, it's not an abstract property of the group, right? It sort of has something to do with sort of how we're thinking of it. And then remark 2 is that because I promised that my talks were going to be about monodromy, this is a monodromy representation. For that to be the case, this mapping class group would have to be the fundamental group of some algebraic variety, but fortunately it is. It's nothing but the fundamental group of the moduli space of genus G curves with n punctures. And so this action on a finite set corresponds to some finite cover of MGN. And what is it? And so the action above corresponds to the finite cover of MGN, and I will tell you which one it is in a second when I get over to this other board. Parametrizing pairs, or maybe I should just say parametrizing maps C prime to C, where C is a Riemann surface of type Gn, and C prime to C is a G cover. That is, it's a Galois cover with group G. So it's a moduli space of covers of curves, and of course the map to MG is just obtained by forgetting the cover and remembering the curve. And it's not, and of course, this is a finite cover because the number of ways to cover a given curve by a finite group is finite. I mean, it has some gigantic degree, which is called a Hurwitz number, but I mean, it is finite. So this is an example of a monodromy representation, like the monodromy representations that I spent most of the time talking about, but it's somehow a monodromy representation sort of a non-abelian kind. Right? Instead of a linear group acting on an abelian group, now we're really acting on the whole fundamental group. We're sort of really taking it in its full majesty and not just looking at its abelianization. And this sort of brings us into, I think, almost completely uncharted territory. So let me sort of try to close by saying what kind of questions we might ask. So, so what can we ask? E.g., you can ask for, maybe I'm going to call this, I don't really have a good name for it. I'm going to call it not very strong approximation. And this would just be the question of, I'm not asking for a surjectivity of any group. I'm just going to ask, is the action of gamma Gn, and I'm going to have to change what I'm about to write. I could write on this finite set transitive. As we saw, that's sort of a strong approximation type question. The answer to this question as I wrote it is obviously no. I mean, for instance, I could take the map that sends everything here to the identity, and that's not going to go anywhere. That's going to be an orbit unto itself. So it's actually it's a little bit complicated to sort of say what you think the orbits should be. So I'll just modify this to say, so first of all, you better say surjective, right? But even that turns out not to be quite enough. So, so let's just say, rather, as transitive as it could be. And these problems are actually typically quite hard to solve. And this is an example, I mean, the example that Kurt mentioned of his talk of the transitivity or near transitivity. There's one case where it has two components, and that's because there actually is an invariant separating them. In the other cases, they're not. And so what Kurt shows in this language can be thought of as some kind of this not very strong approximation property for this particular action of gamma 1, 1 that I mentioned before. And then I guess in this case, strong approximation, I suppose, would mean that the map to the permutation group of, and now I better just say an orbit of the action, it's surjective. That's a bit, I mean, that's a thing that you could ask that would sort of have the flavor of strong approximation. Again, we know very little, but in this context, maybe it's a good time to mention once again the awesome paper of Dunfield and Thurston that Emmanuel mentioned. So, e.g., Dunfield and Thurston, but what they show, you'll see, for the people who really do strong approximation, you'll reject this as a statement about strong approximation, but I'm going to say it anyway because it's related. Show that this is true when n equals 0, so their theorem is about closed surfaces. G is a finite simple group. And now here's the kicker. When G is sufficiently large, relative to capital G. So this is sort of the killer in some sense when we do strong approximation, right? What we have in mind is that there's a single group and we want to say something about it surjecting on infinitely many quotients. Here, for each mapping class group, there's only finitely many finite groups capital G you can use, so it's not really a strong approximation statement for any particular mapping class group, but at least it's. We really don't know, but I think that there is some reason to think that strong, I mean, I don't know, I'm not even going to guess. I think this kind of statement I really think has a chance to be true. This kind of statement I'm much less sure. And of course then, you can just go whole hog. So, and ask about super strong approximation. Why not? But that would be one of the things that you would cut it down by. So, I mean, this is what when I say transitive as it can be, it means you sit in your office and you think for a long time. Oh, this is what I forgot. You reminded me of something I wanted to say. That one way to think of it is you think of all the invariants you can think of, and then you have a set of invariant measures in this finite set that are invariant into the group, and you want to know those are the only ones. I said that for you here. Because I wanted to say something about invariant measures. Did I do okay? So yeah, you think of everything you can think of, and then you sort of hope that there's nothing else. And then, so of course, super strong approximation, about which we know less than nothing, would I suppose be the statement that are the Cayley graphs of gamma gn on orbits, Cayley-Schreier graphs, yes, sorry. Are they expanding? And like, amazingly enough, I will say, I do have one thing to say. There's like sort of like this, as Alex mentioned to me yesterday. There's a kind of an old paper of Pak and Gambard. So Pak and Gambard, given uniform expansion for SL2 FP, yes, but not quite for this action. For the action of the full automorphism group of the free group on HOM from the free group to SL2 FP. So here, instead of calling this the fundamental group of a surface, I'm going to call it a free group. Of course, it was a free group, and now I'm calling it one. And the reason I'm doing that is because the natural group that acts on it is now not the mapping class group, but something much bigger and floppier, the automorphism group with the free group. And this is true. It would be great if it was true for k equals 2, but because that would really be a mapping class group, but there's no hope. This is true for k bigger than or equal to 8. So somehow these automorphism groups of free groups are pretty floppy and can really do a lot. And this kind of stuff, it's usually not phrased this way. It's called product replacement algorithm. But they do show that you get, for this giant group acting, you sort of get everything you want, including the expansion. So I think, I do think this is in some sense like the correct non-abelian or is to fundamental groups as the study of semi-strong approximation for monodromy groups is to homology. Whether we currently have the technology to sort of say very much that's meaningful, I truly don't know, but I'm just, I wanted to sort of promote this class of problems as I think an interesting direction for future work. Okay, so I'll stop there. Thanks very much.